All right, hello. Back at it again with a geometry review. As always, when you're studying for your test, complete as many review problems on your own first. If you're stuck, stumped, then come to the video to hear the explanation. Okay, again, my name is Miss B. If you don't have me as your teacher, the quality is bad, but you got this printed out from your teacher as well. So here we go. Match the description of the events to the likely probability for that event to happen. So I don't know exactly what the numbers are, but they want me to pick values that make sense. Okay. So a short children's book is open to a random page. The probability that the page is numbered between 1 and 10. Okay. That is my event that I'm hoping to happen. So already I'm narrowing between these two because these are both 10 out of something. Okay, well, this one's a short children's book. I think it's more likely that there's 17 pages versus 433 pages. Okay, so I think this one is II. We can write an A. Or we can connect them like that. Ooh, so fun. Okay, a long novel is open to a random page. The probability that the page is numbered between 21 and 31. So again, we've got a 10-page range, but it's a longer novel. I think that goes here. Probability, I select one out of these 10 pages out of 433, length of the novel. Okay, a long history book is open to a random page. The probability the page is numbered between 1 and 100. That one. Okay. There are 100 events in the sample space here, 1 to 100. And there's my long history book. A dictionary is open to a random page. What is the probability? The page is numbered 103. That is only one page. There's only one page. And yeah, dictionary is pretty long, so I think that one. So there we go. I guess I kind of stopped labeling over here, but whatever. All right. One of the letters from the word recklessness is chosen at random. Don't be reckless on your test. Check all your work. Okay. What is the probability that the letter chosen is S? That's how you read that. Okay. One of the letters is chosen at random. What is the probability that the letter is S? Okay. Well, let's see. How many S's are there? Looks like 4. 1, 2, 3, 4. 4 out of how many letters total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4 out of 12. Let's simplify that fraction. Why not? Okay. I know 4 times 3 is 12. So 1/3. They have a common factor of 4. Okay. What is the probability of the letter chosen being a vowel? Our vowels are A, E, I, O, U. Okay. So let's count all our vowels. I'm going to do it in a different color. Or maybe I'll do it underneath. 1, 2, 3. Looks like 3. Let me be really certain. I'm looking really close. Okay, 3 out of 12. Again, I know 3 times 4 is 12. Oh my God. So cancel out the common factor. 1/4. All right. More letters. One letter is chosen at random from the word sample. Then a letter is chosen at random from the word space. Oop, that should say word. Word. How many outcomes are in the sample space? Okay, to find how many outcomes when I have 2 events happening, you multiply them together. Okay, so how many outcomes? This is a 1, 2, 3, 4, 5, 6 letter word. 1, 2, 3, 4, 5 letter word. Okay, so there are 30 possible outcomes. Okay, some other ways that this could be counted, rolling a 6-sided dice would be 6, right? Drawing a card from a deck would be 52. Sometimes we got those spinners that have like 3 outcomes to them, okay? List them in a format of your choosing. Okay, there are so many different ways to do this. The list itself is kind of the most annoying one. I'll show you guys a table and a tree, and maybe I'll show a list. Okay, for a table, I've got 2 different outcomes, right? Or no, rewind. I have 2 different events. The first event is choosing a letter from sample. Second event is choosing a letter from space. So I can make a table here. Okay, need 6, so 5 lines. And 5, so 4. Okay. Oh my goodness. I got too excited. S A M P L E S P A C E. All right. I could choose S and then S. So SS. I could choose A and then S. AS. MS. PS. LS. ES, right? This is my first event, is choosing a letter from here, and my second event is choosing a letter from space. So this would be S P A P M P L P E P. Okay, I kind of stopped narrating because it's just the same thing over and over again. All right. So that is a table. That's one of our possible formats. Okay, another format could be a tree. I'm actually going to grab scrap paper so I don't get this too messy. Okay, we could also use a tree diagram. So sample and space. Okay, I've got my letters for sample listed out. So if I choose an S for sample, then an S, P, A, C, E for space. Okay, so I could go S then S, S then P, S then A, S then C, okay? Like that. I need to move these and give myself enough room. So S, A, M, there you go. So there could be a tree diagram, right? Because first we're picking a letter from sample. So picking from one of these letters. And then from there, we're picking a letter from space. The other method you can use is just straight up list them all. SS, SP, SA. Okay, you can literally just list them all out. Cool? All right, what is the probability the letters chosen are A, A? Okay, there's only one outcome possible there. Okay, you can see from our chart, if I choose A and A, there's only one possible outcome out of the 30 total. So there's our probability. Explain your reasoning. One outcome out of the 30 possible in the sample space. Okay. A district is interested in attendance for students in middle and high school. Okay, the results for one day are summarized in the table. So, let me zoom out a little bit more. Whenever I see a table like this, my very first thing I do is draw lines to separate the total from the other information. Okay, just so I don't get confused. So, describe the meaning of each of the probabilities below. Okay, this is the probability a student is absent. Probability a student is absent. Well, let's look out of all the people absent. 3394 out of total 22589. Okay, this one is asking the probability a student is in high school. All right, so let's look at all the high school students this time. 12681 out of 22589. All right, this one is asking, what is the probability a student is in middle school and present? That's what this little symbol means. It means and. I think of it like the N in the word and. Okay? So in middle school, these are all my students in middle school. Here, why don't I circle? These are all my students in middle school, and these are all my students that are present. The and is where they overlap. So these 8,000 something students are the ones that are present and in middle school out of our total 22589. This one here is asking the probability a student is in middle school or present. Okay, so think about some of the examples we did in class. We did the one that was the coffee with cream or sugar. Okay, some people put just cream in their coffee. Some people put just sugar in their coffee. Some people put both cream and sugar in their coffee. So all three of those options are encompassed in that word or. So all of these, anything circled here is counted in or. Okay, so, oh, I need a calculator. 8632 plus 1276 plus 10563. I don't know why I'm saying my numbers so weird today. And I'm still out of the overall total. I'm just adding these up. Okay, we got 20471 out of 22589. All right. Last one of this, not of the whole packet. What is the probability a student is absent given, that's what that symbol means, that vertical bar means given or under the condition, okay? So probability a student is absent given they are in high school. So I'm just looking at those high school students. I'm looking at the probability a student that a student is absent given they are in high school. I'm only looking at those high school students. So here, I'm restricting my view to just the high school row. That's what this given is doing. It's restricting your view. So the probability a student is absent, okay, well, that'll be the 2118 number out of the total high school students. 12681. I've been telling my students, I kind of think of this almost like the fraction bar, where the total amount of high school students should be your denominator. Okay, that is the only time in a two-way table where we're looking at an overall total that's not the overall total, okay? Is when I have a condition or a given statement. Next picture. Students were asked about their participation in after-school activities, and the results are shown in the Venn diagram. M is students who studied music. S is students who play a sport. So label what each portion represents. Okay, this is music. This is sports. This is music and sports. This is no music and no sports. All right, I kind of need to know how many students total were included in this in order to do any probabilities, right? Actually, I might as well turn this into a two-way table because I'm seeing, hold on one second. All right, I'm back. I was just getting a little formula sheet set up. Okay. These are our formulas that relate and with the condition, the given, okay? You could turn this into a two-way table and figure out your conditional probability from there, but I'm going to do it where we're using these formulas, okay? But we'll get there when we get there. We labeled the Venn diagram. What is the probability a student studies music and plays a sport? Okay, first I need to figure out the total number of students. So I'm going to add everyone up. 25 plus 12 plus 25 plus 78. 140. So I have 140 people total. Okay. What is the probability a student studies music and plays a sport? It's 25 out of 140. And let's get that as a decimal, okay? So that's about 17.9%. Or get it as a percent, sorry. What is the probability a student does not study music? Okay, this is where we need to be really cautious. This whole circle are all students that study music. So anywhere outside of the circle is where I'm looking for not music. Okay, this whole circle are students that study music. So for not music, I'm going to take this 25 plus this 78. The 103 out of 140. If I asked you for a percent, you would say 73.6. All right. What is the probability a student studies music given they do not play a sport? Given they do not play a sport. Okay. I'm going to use this formula. Okay, either one, they're the same. But because they're asking me for this with the vertical line, the given, I'm going to use this one because it's already all by itself, right? So if I use this one, I would have to solve. Okay, so probability of music and not a sport is equal to the probability of music and not a sport over the probability of not a sport. Okay, just taking this formula and plugging in my letters instead of A and B. Okay, so the probability of music and no sport on the top is this 12, right? Just the 12. This 25 is also playing a sport. Okay, so 12 would be music and no sport. 12 out of 140. Probability of not playing a sport, that would be everything outside of this green circle. So 12 and 25. Let's do it off to the side. 12 plus 25 is what, 37? 37. So 37 out of 140. Okay, we have a fraction and a fraction, so we are going to keep change flip. 12 out of 140, keep the first fraction the same, change to multiplication, flip the second one over. 140 on top and bottom. So 12 out of 37. About 32.4%. Okay, you could have figured this out without using the formula if you looked at the probability of students that play music out of the 37 that do not play a sport. So 12 out of those 37. I just want to show you guys the formula, mostly. But you could have gotten this by also just looking at, okay, the 12 out of 12 plus 25. Okay, and we got the same thing. That's the beauty of these formulas, is they always work. So if you're like stumped, you can always use it. Okay, maybe we'll do this one without the formula. What is the probability a student does not play a sport given they study music? So I'm looking out of the whole music group. So 12 plus 25, which also happens to be 37. Out of everyone in music, what's the probability there's no sport? So that's also 12. Out of everyone in music, see, out of everyone in music, what's the probability they don't play a sport? So out of everyone in this orange circle, these 12 do not play a sport. So 12 out of 37. All right. At a middle school science fair, all of the science projects used mathematics, but only 30% display the mean or the median. I show my students to put a box around if you have and or. 27% display the mean, 16% display the median. Okay, apply the addition rule to determine the probability that a randomly selected project displays the mean and the median. Okay, this is our addition rule. Whoops. Make it look a little. This is just scrap paper, guys. This is our addition rule. Okay, I think we learned this version. Oh my gosh, focus please. I think we learned this version in class, but I know my class was talking about how you could swap the and the or and they're still mathematically correct. Okay, so if I'm trying to find the probability a project displays both the mean and the median, well, the probability mean and median is equal to the probability of just the mean, so 27, plus the probability of the median, 16. I guess this isn't just the mean. I keep saying that, but that's not true. Because some of these could be mean and median. Anyway, probability a project includes the mean, plus the probability project includes the median, minus the probability it includes mean or median, so minus 30. So 13%. Okay, use a Venn diagram. Let's do it. Okay, be sure to put your Venn diagram in like a little box here so we can put the outside part. Okay, so let's say mean, median. This is both. And this over here will be neither. Okay, so mean and median, that is our 13%. Mean only. Okay, well, 27% have the mean, minus those 13 that have both would be 14% have the mean only. Because remember, this whole circle needs to add up to 27%. Okay, so for the median, 16 minus 13 is 3. So 3% display the median only. And then we need to make sure we account for projects that display neither, okay? So 100% of projects, right? Because 100% means everything. So minus 14, minus 13, minus 3. $70 70% displayed neither? Guys. I'm just kidding. This just says mathematics, not statistics, so. Okay, this is not automatically 27 here. This whole circle needs to add up to the 27. Oh my God, there's so much more. Soccer team has 2 games in 2 different days against different teams. A is the soccer team winning the first game. B is the soccer team winning the second game. So what does it mean for the probability of B given A? Okay, the probability that B is they win the second game. So probability that the team wins the second game given they won the first game. Okay. Do you think A and B are independent? This is kind of a opinion one. Okay. Maybe not, right? Maybe we could say no, because they're playing 2 different teams. Right? Like maybe we don't know one based on the other. Okay. But if maybe you're sitting there saying, Miss B, yes, they are related. Or maybe they are independent, because if they're good enough to win the first game, then maybe there's a better likelihood they win the second game. If they are good enough to win the first, they may be more likely to win the second. Okay, I could see an argument for both sides. And this is one where it's not as clear as like flipping a coin. Okay, if you flip a coin in succession, like over and over again, of course those are independent events. The first coin flip is not influencing the second one. But because there's skill here, I can't really tell if they're independent or not. So I would need to confirm it mathematically. So if the events are confirmed to be independent, how are probability of B given A and the probability of B related? So if independent, then those two probabilities are equal. I know it's kind of weird because we swapped A and B, but that is our independence test. If this is true, then those two events are independent, if those values are equal. Okay, a large aquarium has 48 guppy fish in it. Table summarizes fish based on color and sex. Okay, I'm noticing right away there's no total column. You can always add your own. Okay, there's my total. Whoop. Okay, so 5 plus 12, 17. 13 plus 18, I think that's 31. Okay, make sure that you check that the totals add up going up and down and side to side. Okay, if a guppy is selected at random from the aquarium, what is the probability it is both blue and female? What is going on? Okay, that's better. Why did I not do that sooner? So both blue and female, that's this 18 out of 48. 18 out of 48. Be sure you can convert that to a percent or a decimal. I think most often it'll be a fraction or percent. This is 37.5%. Okay. What about probability? It is male or orange. Okay. Male and orange. Let's draw our circles. So here's male, here's orange, everything that's been circled. Okay, so 12 plus 5 plus 13 out of 48. 30 out of 48, which is 62.5%. All right, find the conditional probability. The probability a fish is female given it is blue. All right. So looking just out of the blue, probability of fish is female, 18, given it's blue, 31. 18 out of 31. Again, this means just look at the blue column. Just look at the blue column. What is the probability that a fish is female if I'm only looking at the blue column? That's 18 out of 31, which is, whoa. Calculator's being wacky. About 58. All right, last page. 200 Carolinians, woo, were asked which state they lived in and whether or not they lived on the coast or more inland. The results are in the tree diagram below. Okay, so here is like the root of the tree. Splitting up, it looks like, okay, well, 200 people total were asked. 90% of those people were from North Carolina, or not 90%, 90 people. 110 of those people were from South Carolina. Oh my goodness gracious. Okay, so out of those 290 were from North Carolina, 110 were from South Carolina. Okay, of those North Carolina people, so just looking at this column, 36 of them were inland, 54 of them were on the coast. Of the South Carolina people, 44 of them were inland, 66 were on the coast. Okay, then we can just add across 80 and 120. And again, I always check, yes, 80 plus 120 is 200, good. All right, complete the table, done. This is our tree diagram like we were doing earlier on that scrap paper, right? Mine just looks a whole lot uglier than this one. All right, use the probability of being coastal, given you live in North Carolina, to determine if living on the coast and living in North Carolina are independent, okay? So let's find this first. Probability, they're on the coast, given they're in North Carolina. Okay, so again, I'm limiting to just the North Carolina column, just this column. So being on the coast looks like 54 people out of those 90 people in North Carolina are on the coast. All right, let's get percent. Oh, it's not even approximate. It's exactly 60%. Okay, now to check if they are independent, I need to compare the probability of just living on the coast, just that first part of our condition. Okay, because if the probability of being on the coast is the same probability as being on the coast in North Carolina, then it doesn't matter if you're in North Carolina or not, because the probability of being on the coast is the same either way, whether you're in North Carolina or not. Okay, so probability of being on the coast in general is 120 out of 200, which is 60%. Yo! They are independent. Yes, the two events are independent. Because the probability of living on the coast is the same as, whoa, the probability of living on the coast given they are in North Carolina. Okay? So now they want me to use the probability of being inland and in South Carolina to determine if they are independent events. So this is our other test for independence. These are our two tests for independence. Okay. Here's the one we just used. Here's the one we are about to use. Let me fold it. Hold it up. And the bell's about to ring. Yikes. All right. So if this is true, let's see this. Probability of being inland and in South Carolina. That is 44 out of everybody. Okay, I'm not changing the total. The total should be out of everybody because I don't have a condition. Okay, or a given statement. Okay, inland and South Carolina, 44 out of 200. Which is unknown. 22%. Okay, the other part of this formula is we take the individual probabilities and multiply them together. So let's see that. Probability of being inland times the probability of being in South Carolina. Okay, so probability of being inland, 80 out of 200, times probability of being in South Carolina, 110 out of 200. Multiply across, 80 times 110, 8,800, 200 times 200. Whoa, these are big numbers, guys. My students are coming. 22%, what? They're independent too. Yes. The two events are independent. Okay, and here's my final like mathematical justification. Probability of living inland times the probability of being in South Carolina is equal to probability inland and South Carolina. All right. There we go. Finished. 6 hours starting, so I gotta go. Happy studying. You're gonna do great on your test. Ask your teacher for questions. Hopefully you're not watching this literally the night before. I know some of you are, okay? Ask your teacher questions. Good luck.